Hi guys, welcome to Hutsons-Hacks. Today we're going to talk about another R package that I've managed to get onto the CRAN universe. This one's called FeatureTerminator, and I've purposefully used the Terminator writing in the logo as well, with a little robot Terminator. So it's an R package that's been created specifically to remove unimportant variables from statistical and machine learning models. A lot of the feature selection tools, they don't do this automatically. They allow you to do this manually. So what this package does is it gives you the option to do this automated or to remove it yourself. Okay, as I said, this is part of the Hutsons-Hacks tutorials. Please hit subscribe if you like this and follow me and leave comments on my Hutsons-Hacks website or over my GitHub. If you've got any issues, then go onto the GitHub page and raise it there. I'll provide a link to that afterwards. But as you say, let's get going with the tutorial. Okay. So I've got this pre-prepared markdown document that I configured earlier, just for the sake of brevity and clarity. So what we first need to do is load our package, FeatureTerminator. And if you need any help on the package, you can just go to the FeatureTerminator documentation. You'll find it in relation to the specific methods. Let's go down to like the references where it's linked to. That's the caret library. How you pass arguments and how you use it will all be in the help file. So let's run the setup. So let's load in our packages. Okay, so what I've got here is the FeatureTerminator package. I'm going to be using caret. You can use tidy models if need be. I'm going to use dplyr as well, ggplot2, and the random forest package. So on the associated website and blog and the associated vignette, I go into what the package contains and all the nuts and bolts behind the package with a little bit of statistics. I've tried to keep that a little bit light. So the two main functions at the moment that I've got implemented in the package are recursive feature engineering or a feature elimination. So I'm going to eliminate the features as a feature selection method. We've also got another method which looks at removing high correlated variables, so multicollinearity, and fixes that problem as well in statistical models. So it can be used in ML pipelines or statistical model contexts as well. So first of all, we're going to train a data set, and I'm going to use the standard iris data set. I know for tidy models they prefer Palmer penguins. I'm going to use iris because it works quite well in this example. So for you anyone that doesn't know the iris data set, I mean probably very few out there now. If you're first coming to machine learning, you might never used it. Most people will have. So it's a study conducted by Ronald Fisher, around different species of plants, and he tried to perform a classification of the plants based on these 4 independent variables, so sepal length, sepal width, petal length, and petal width. And what the aim is to actually do is, you'll see this in things like linear discriminant analysis, so look that up if you've never heard of that, to reduce dimensionality. Here what we're going to do is we're going to try and classify the species. If you were doing a machine learning pipeline. This part of the tutorial, I won't go into training models. What I'm going to go into is the feature selection techniques. So they are models in themselves, but we're not completing the full machine learning pipeline. If you want to learn how to build a classification model from end to end in tidy models and caret, I've got associated videos that will help you achieve that on my YouTube channel. Okay, so back to task. So this is the iris data set. And if I print it out, you can see now in my first feature engineering. So if I print out the data, we've got it there. So what I'm going to do now is I'm going to pass the recursive feature engineering terminator into my model. So what I'm going to want to do is I'm going to say in my data frame that I've just saved into memory, the independent variables, the ones that I want to check for unimportance in predicting our y, the 1 to 4 variables, you can do it by the name of the index as well, and I'll show you how to do that in a second. So we're going to slice the first 1 to 4 columns, and then the fifth will be our species, the thing we're trying to predict or classify in this instance. So all you need to do is pass in your data frame, the X columns, the Y column or cols. We're going to specify an altered data frame. This is a Boolean logic, so it will essentially return a data frame that's been altered as a list. And then we're going to use the eval function. So what we're going to use is random forest feature importance variable selection in this particular instance. Please refer to the documentation around the different methods. There's naive Bayes selection. There's tree bag selection, which is a classification tree. Bagged, so it's a bagging approach, which is a way that you can improve model accuracy. There's a linear method as well, which looks at least squares. So, but here we're going to use the random forest functions. Again, this is all explained in the supporting post that's going to go alongside this. So you can see that I've got these random forest functions, and what it's going to do is look at the variables that have less of an effect on the mean decrease in accuracy. So the ones that have high effect on the mean decrease in accuracy, they're going to be routed down as less important. So then what we're going to do, again, there's the links to how you evaluate feature importance in random forest models in the blog post itself. We're going to use this. So we're going to fit this FeatureTerminator object, so recursive feature elimination object. So this is the first approach, the first method, by doing it by the column index. There's also doing it by column name. So the X cols I'm still going to do 1 to 4, but the Y col this time I'm going to pass in species, which is the thing I'm trying to predict. And at this stage it's a factor. I've already done the conversion to a factor. Again, we're going to alter the data frame, and if you don't pass the eval funcs method parameter into the function, essentially what will happen is it'll just default to the random forest feature selection technique. And then a further example, the longhand, would be specifying this way: ref x col name, the recursive feature elimination terminator, passing your data frame. Pass the x cols as a vector of column names. If there's more than one, you need to put it as a vector. And pass the y cols as the species name. And a note here, this is a shorter statement apart from the column names. This is also missing the altered data frame. So actually that's defaulted to true. You'd have to switch it to false if you didn't want to produce the list item with the altered data frame as well. So if I run those lines, it's going to do the fits and it's going to do my recursive feature elimination in each of those ways. Essentially, they're doing it is performing the same test. So you get a warning message once that's been fitted, well, an information message, shall I say. Removing features as a result of recursive feature engineering elimination. Expose RFE reduced data from return list using selectors, so dollar selectors from the list. IV selectors, so the optimal variables are petal width and petal length. So actually you don't really need the sepal length and sepal width to predict the species of the flower, it turns out, using this methodology. Okay, so let's explore the model results then. So what I'm going to do is, as a list item, my fit is called, I'm going to use this first one that I created. These are just the same copies but different implementations. I'm going to use the RFE fit and I'm going to return my model results. So you can see that it's done some cross-validation, so tenfold cross-validation, so some resampling. And by all those resamples, it's worked out that via the recursive feature elimination method, that the two variables that have the most predictive importance on predicting the species are petal width and petal length. If I wanted to see those, the fit results as the most actually here. So I'm getting tongue-tied. If you want to see the most important variables in terms of the accuracy and the effect on their accuracy, you can see that actually just having those two variables in there results in an accuracy prediction of 96% based on our data. We're training this on the full data set. We're doing the feature selection on the full data set. You can also do this on the training data set. And again, refer to my other tutorials around different types of splitting methods in Carrot and Tidy models. There's a tutorial for either or. So again, we're getting good accuracy there, and our kappa rate is really good for that one as well. So actually with this means the kappa is a Cohen's kappa rate. It means for unseen observations, this is an estimate of how well the model will perform in the wild. So with unseen data, that's how well it thinks it'll perform. And then we can print out the optimal variables from that list. So it's RFE fits, atomic selector selects the list item, RFE model fit results, and then the optimum variables. And you can see we've got petal width and petal length returned from that. There are some other results in there. So if I go RFE fit, RFE model fit results, you can see that I've actually got the best subset, I've got the variables that were passed, and the number of folds and resamples there. I can expose that. I can look at the results. Again, that's the same as this. It'll automatically print that when you do optimal variables. So I've already printed all the model fit results. Things like the control, if there was a control passed in Carrot. So actually that's just printing back the function, which is not that helpful. The resample. So yeah, you can see that these are the resamples, the kappa rates, and what is calculated the accuracy at those number of variables in each resample. Then by the optimal number of variables, it's going to take a mean estimate of that resampled rate to come up with the mean accuracy of all those resamples, and that's how it does it. It collects the resamples that way. Again, refer to my Carrot blog on this. So that's what it allows you to do. So it'll allow you to explore the model fits. So that puts in the original and the reduced data then. Because we set that altered data frame to true, we're going to have a data frame list item from the RFE fit object. We'll have an RFE original data, so the original data that's passed through to it, and an RFE reduced data that's passed to it as well. So you can see that the reduced data, we've got sepal length, sepal width, petal length, petal width, and the species. Here, the reduced data after doing recursive feature elimination, you can see that we've only now got a data frame with the petal width, the petal length, and species. So actually that's automatically done that removal for you. So there's two methods you can have in the manual process where you eliminate the features yourself by doing things like dropping variables in dplyr or using dplyr select, etc. Or you can just let the model and algorithm do it for you, select the optimal number of features. For certain models, they'll really like you for that because you won't have to do things like dimensionality reduction, techniques such as principal components analysis, and DB scan and more advanced nonlinear methods. Okay, so that's the recursive feature elimination method. Another way to do it would be to remove highly correlated features. So actually, in certain models like linear models specifically, you will have issues if you have lots of correlation in your models. Some nonlinear models don't suffer from this, but this kind of caters for that in terms of the linearity of the model. So if you've got that correlation, it will affect the overall coefficient of determination for the model, i.e. the R squared. It'll either inflate it or reduce it, dependent on the particular scenario. So here we're going to do a multi-correlarity term fit. So we're going to fit our feature terminator, multi-col terminator. We're going to fit it to the same DF that we've been working with. We're going to use the same columns that we've been working with. We're going to specify the y cols equal to species. We're going to alter our data frame to do the same automation, so selection of the optimal data. I'm going to set a correlation significance, so say that we want to filter out anything that's greater than 90%. Okay, so based on that correlation significance cutoff, it's going to print out when it finishes that this has finished removing features as a result of your cutoff. And then to explore the quantiles, so the range of the correlations, we can produce a correlation range chart, something that I've knocked up that's relatively unique to this. So all it is a horizontal bar chart, and under the hood it's got the quantiles cut off. And what it's going to look for is the proportion of the data with the highest correlations here. So you can see that actually by doing that method, cutting off the 90%, we're probably excluding about the 85th quantile, so around about 15 odd percent of all the data is being excluded based on that factor, or 15% of the correlation in the features, the correlation raw scores, is being excluded. Again, that's if you didn't want to go that low and you wanted to enhance the correlation slightly, so say 95%, and then you wanted to explore the quantile chart again, you can see that actually the bars keep moving. If we go ultimately up to about 99%, you wouldn't expect any of the features to be that correlated. So you're going to get an error. It's going to say that no, there's no real significance to that level. I'll keep it at 90% because that's quite a nice cutoff. Anything higher than that I want to be excluded from my model to avoid that, like say, effect and overinflation of the coefficient of determination, aka the R squared. Okay. So if you want to visualize that in terms of the raw correlations in the data, so this will be in the independent variables, excluding the dependent variable. You can hit the play button here, so you can expose the correlation matrix. You've got the correlation matrix, you can see that actually petal length and width have got a high correlation there, about 96%. Is there any high negative correlations? Not really in this data. They seem to influence each other in a positive direction, not a negative direction. But as you can see, the chart actually caters for both sides of the correlation cutoff. So it will look for negative high correlations versus positive high correlations as well. So also underneath that, we've got the covariance matrix. So actually how one variable causes the other to move in a positive or negative direction. And the effect of that movement will also be estimated in the correlation. So this is more around a raw score of how much to quantify the impact of one variable over another. And then you can print out the actual quantiles themselves. So I've done them in 5% intervals, 5, 10, 15, 20, 25%, 30, 35, 40, 41, etc., all the way up to 100%. And I can actually see that around about your interquartile range, your positive correlations around about 35, 0.35. Around your third quartile, you've got about 87.1%, or 0.871. Around 85%, it's about a 90 correlation. So you could actually even say, instead of having a correlation cutoff, just exclude the 85th quartile, or above the third quartile here. Again, there are methods that you could then utilize on the back of this. So once we've done this process, I'm going to then get my new, and this is a very long data frame name. I wouldn't recommend you calling your data frames something this long, but it's then going to return a data frame for you, and it's going to do the fits with all our features removed. And you can see that actually with that correlation cutoff, whereas before we had, and if I expose the data frames here on the right hand side, you can see in the other method we had 2 variables left. This one, so 2 independent variables left. It cut off the petal length and width altogether. now we've got petal width coming through as well as sepal width and sepal length. So now you can then, like I say, explore in terms of different cutoff features, but it allows you to then cut off those multicollinearity effects. You can do some more analysis looking at things like QQ plots, plotting out the residuals, etc. Right, okay, so that takes you up to what's included in the package thus far. What am I building next? So what's in the pipe, what's in development? So simulated annealing methods, which is a probabilistic technique for approximating a global optimum of a given function. It comes from metallurgy, an annealing method, which is a technique involving heating and controlled cooling of material to increase the size of its crystals and reduce their defects. In terms of statistics, it's looked at the optimal search space, so it's an optimization technique that can be utilized for feature selection. I put a link into the statistics and the descriptives a little bit more in the blog post because I'm better at writing stats than sometimes getting it over via video. And lastly, regression, so it's a regularization method that allows for the intercept to equal 0 or approximate 0, should I say, meaning that any variable that gets close to that is probably of little or no importance to the predicted y-hat measure, so the thing you're trying to predict, so the y-dependent variable. So that's a way that you can do feature selection, and I'm currently working on that one next. So those two will be in the next version of the package. But yeah, please download the package from CRAN. Give it a thumbs up, get downloading it. Also, if you've got any issues around functionality, please feel free to go to my GitHub page. So I'll just say that it's GitHub stats Gary and it's the feature terminator. To raise an issue, you can just go to issues and then add new issue. And then I'll answer that as soon as I can and get back to you. Okay, and there again around installation, if you need help with the installation, and it's very new because it's not even been downloaded yet because I've not launched it. So how you install the package from GitHub, how you get it from CRAN, how you load the package into your environment in R, how you use recursive feature elimination. I don't know why I keep calling it engineering, but it's the same thing. It's actually engineering features. Remove very high correlated features, so the multicollinearity terminator. And then that shows you how you can pull back your reduced data frame. And the vignette that supports this also shows you how to work with the package with more descriptives around that. And there'll be a post on my Hutsons-Hacks website around how to work with this better. So it's been great taking you through this, and please subscribe. Please hit like if you like this video on YouTube. Please put a comment on my Hutsons-Hacks site. Please, if you've got any issues, raise an issue with GitHub. But yeah, have a great day, guys, and stay safe, and I'll see you soon with hopefully another update to this package.